We'll wait for 2 more minutes and then we'll start. Let us see whether someone else joins or not. Okay, let us start today's class. So today is 7/11. Okay, before proceeding to the first question, let us refresh the past 2 to 3 lectures. We already have studied in the previous problem solving session about the transient heat transfer and about lump parameter model. But in the previous few lectures, sir have already also taught about fin, right? The extended surfaces. So we'll get a brief detail on that before starting to the problem solving session today. So this is the week 3 of problem solving session for the heat transfer course, whose principal instructor is Professor Sunando Dasgupta of IIT Kharagpur, and myself Kalpita Nath, and I am research scholar at IIT Kharagpur. Okay, so let's share the screen. Uh, can anyone confirm whether the slides are visible or not? Are the slides visible? Okay, and the note page, that is visible as well? It's not. Okay. Just okay, now it's visible. Both of the screens are visible. Okay.
Class 3, ma'am.
What?
We are able to visible class 3. Is it
Yes,
correct?
yes. Yeah. Both of the one is the presentation slides and another is the notebook where I'll be explaining
Okay.
everything. Okay.
Ma'am, one more doubt, ma'am.
Yeah. Tell me. Hello.
Hello.
Yeah.
Ma'am. Ma'am, assignment 3 is not visible, ma'am. So what can we do?
What three?
Assignment number 3.
Actually, another two days are allotted for that. You can find the mail ID in the course itself. You can ask them out. You can mail them. I am not allotted for that, for your regular
Okay, okay.
assignments. Okay.
Thank you.
You can even mail to the NPTEL IT Kharagpur section or the main IT Madras NPTEL. They'll sort that out. Okay. Okay. First about fins. So we have already seen in class that uh, fins are the extended surfaces that we basically use for extracting the heat of a surface, cause it provides us what? It provides us more area for the convection to happen. Okay. So where the fin is attached, like if we have a fin attached like this, like this, where fin attached and conduction is taking place in this side, in this direction, right? And this is x. This is the base temperature Tb, and this is the width of the fin, and this is the thickness of the fin. Okay, and from here everywhere like convection is taking place. Hmm. So this is just a straight fin of uniform cross section. As sir has already told, there are different kinds of fin. There will be fin where cross section even will be changing, or the annular fins like that. So first of all, we have learned about fin efficiency. Uh, and before that, we will know about where the fin is attached, that is at x equal to 0, that is at this point where the fin is attached. We will have like at what rate the heat is extracted. That will be given by the conduction equation, that is minus K. AB is the this area, this is AB, and dt dx at x is equal to 0. Okay, this will be the heat that is transferring in this direction, that is being extracted by the fins. So first of all, the fin efficiency, we have two terms for fin, that is one is fin efficiency and one is effectiveness, right? So for fin efficiency, what is that fin efficiency? So that is actual heat transfer upon heat which would be transferred if the entire fin was at base temperature. That means if we like when we will move in x direction, so obviously as we will move in x direction, the temperature will decrease gradually. Like if this is the base temperature at the surface, when we will attach the fin, the temperature will reduce, and it will eventually, if the fin is long enough, it will be close to the temperature of the ambient, that is T infinite, right? So if we consider that if there is no decrease in temperature and the entire fin is at a base temperature, so the actual that heat is transferred and the heat that would be transferred if the actual like if the whole fin is at the base temperature, that gives us the fin efficiency. That is how much efficient is the fin for extracting out the heat. If it will be efficient, then only we'll be using it, right? And another is fin effectiveness. So that is fin heat transfer rate upon the heat transfer rate that would exist without the fin. So what is this? The fin, the heat transfer that will be like, that is the heat that would be extracted by the fin upon, if the fin won't be there, what the heat transfer rate would be. So if this is not high enough, why would we like we will be spending extra cost in fabricating the fins? We won't be, right? So that's why its value should be greater than equal to 2. And as sir have already shown in the class, is it can be written as K P H AC upon half, to the power half. Okay, so for this to be greater than is equal to 2, its value should be more than equal to 2 in order for us to fabricate fin on the surface of a like of any body, right? So K should be, first of all, this K, that is thermal conductivity, should be large enough. And thermal conductivity depends upon the type of material that we'll be using. And if the thermal conductivity is large enough, then the entire fin temperature is going to be close to the base temperature, that is the temperature of this surface, right? If the thermal conductivity is large. It won't be exactly equal to base temperature. There will be some losses, but it will be close to that. So we will try to choose a material that will help us to get a higher value of thermal conductivity. H should be less, heat transfer coefficient. So obviously for liquid, between the liquid and solid, the heat transfer coefficient, if the liquid is there, then heat transfer coefficient will be high. So we in most of the practical cases, we see fins are being used for like gases, like when solid from solid we will be trying to extract the heat in the ambient atmosphere, right? For liquids we don't normally use fins. So H we want to keep low. That's why for air or like any other gases, we normally tend to use fins to extract the heat. And another is P upon AC. What is P? P is the perimeter and AC is the cross-sectional area of fin. So for every ratio of the perimeter to cross-sectional area should be large. That means we are going to need a larger number of thin films attached to the solid surface from where you would like to extract the heat. We have also read about uh, the equation that will be used for fin, that is d square t. I won't be going for the derivation, it is already available in the class. So 1 upon cross sectional area dAc dx dt dx. That let me tell you, like from where that came. That came from, if this is a like cross sectional area of the fin is changing, like if this is the fin and this small cross sectional area we are taking here. Then this is qx and this is qx plus del x, right? And from here convection heat transfer taking place, that is dq convective, and this is the conduction heat transfer. So the equation will start as qx plus del x for this small element of solid, right? From where he like that is the part of the fin. So this is the main equation from where we found out this. So then this is 1 upon AC cross sectional area into h upon k das upon dx, this surface, the area of the surface. This then t minus t infinite is equal to 0. Now let us consider if the cross section area of the fin is considered as constant, as here, if the cross sectional area is constant, then dac upon dx is equal to 0. Then let us consider t minus t infinity as theta, and AC is not a function of x, as we have seen, like we have seen that the cross section area is constant, so it won't be a function of x. Then the equation becomes, we can write das upon dx, that is considered as the perimeter, and as is equal to, is can be written as p delta x. So the equation becomes d square theta upon dx square. This equation becomes d square x theta upon dx square minus 1 upon cross sectional area h upon k into p is equal to 0. And this we can write as, theta will be there, this we can write as m square. So d square theta upon dx square minus m square theta is equal to 0. So here obviously it can be solved as theta x is equal to c1 e to the power mx plus c2 e to the power minus mx. So we need two boundary condition, as there are two constants available. So first one we can write as theta at 0 is tb minus t infinity is equal to theta b. Now we have we can take like four conditions here. First one is if fin is very large. For that at x is equal to infinite, t will be is equal to t infinite. And if fin is considered as short, then at x is equal to 1, that is the entire fin is going to be at constant temperature, that is the base temperature. So at x is equal to 1, t is equal to tb, and this is at x is equal to, x tends to infinite, t tends to t infinite, t is equal to t infinite. And third is if the fin tip of the fin is a diabatic. So for that it will be d theta dx, that is the temperature won't be there, there won't be like the, for the change in temperature, that will be constant, as the system is a diabatic now, the tip of the fin is a diabatic, so there will be no heat transfer over there. So at x is equal to L. And another thing is if temperature is specified, at x is equal to L, theta is equal to theta L. Okay, these are the four conditions that can be considered. So this is a brief of that has already been taught in class. I'm not going to further details. Let us proceed to the problem solving session today, and I'll proceed to the first question of today's class. So this is the first question that is visible on your screen. We have just studied about this. I think you can answer this. Just tell me which option will be correct here. Anyone? Anyone who wants to answer, or you are having any doubt? Yeah, it's B. So let us proceed to the first. So boundary conditions will be at t is equal to t naught, t will be t naught at x is equal to 0, and at x is equal to L minus k dt dx is equal to h t minus t ambient. Here conduction at the tip of the fin, the conduction will be is equal to convection for any finite fin. This condition is valid. So answer will be option B. Now let us proceed to the second question. Anyone who is going to answer this? This is relatively easy. I have already taught this in the previous class, the introductory portion. Yeah, that's it. Okay, let us have a bit of recap what is happening. So for we have already seen that in the previous class. Still, for the Lund parameter model, theta upon theta I is equal to t minus t infinity. We already know this, ti minus t infinity is equal to exponential, just 1 second, exponential HAS upon rho VCP into t. Now tau t is equal to rho VCP. This we are writing here HAS. That is the thermal time constant. This we can write as 1 upon HAS into rho VCP. Now this thing is the characteristic length for any body, right? So this we can write as LC. So this formula we can write as now rho LC CP upon H. Now if LC will decrease, that is the characteristic length of a body is less, then this whole time constant is will be less. Like if there are two bodies, one has characteristic length small as compared to the other, then obviously it will get like the temperature will get reduced faster as compared to the other one that is having larger characteristic length. Remember this, and based on this, let me give you one simple question that will help you clarify this thing, right? So let us have three bodies that have same initial temperature, same mass and same material. Just the structure of the bodies are different. One is a cube. Let us consider that each side of the tube is R, right? And we have a sphere. Let us consider its radius to be R as well. And there is one cylinder. Let us consider its radius to be R. Now, the question is, which of these three bodies will cool faster? Give me a quick answer for this. This will be based on characteristic length, as I have already said. Anyone? Where is Shanchita today? She is not answering. Normally she answers. Anyone who is going to answer? Cylinder, are you sure? Tell me about how you think that is cylinder. Uh, no. See, it doesn't depend upon surface area alone. It depends upon the volume as well. So characteristic length will be depending upon, as I've already said here. Here we can see, right, that characteristic length is volume upon the like surface area. So on this, the whole thing will depend. So not only just the surface area, it will depend upon the volume as well. So we have to find out the characteristic length for all three. And based on these three, the one that will be having the characteristic length minimum, that will be cooling faster. Yeah, correct. Q. Okay. How? I don't think I have to show you the characteristic length, how to find out. So yeah, if we have already found, you know that the characteristic length of this thing, this has 6 surfaces, so 6a square, right? So surface area is 6a square or r square as well, like as a is r, the side is r here, and the volume will be r cube, right? So this will be r by 6, the characteristic length. For this, it will be r by 3 for the sphere, and for the cube, it will be r by 2. So as this is minimum, so obviously the cube will be the one that will be cooling down faster, as it is time constant, thermal time constant will be minimum. So now let us move to the this question number 2. For this, we have to find out what are the two numbers that will give a combination of the time constant. So for that, we have to take the time constant into consideration, that is MCP, HA, that is rho VCP upon HA. So T upon tau is equal to, this is T upon tau, right? Here, T upon tau. So this we can write as THA rho VCP, and this we can write as T upon rho Cp Lc upon H. So this is K upon rho Cp into T upon Lc, we can write this as that, into HLC, like we are just rearranging this, nothing else. And this is obviously alpha. So this we can write as alpha T upon Lc square, and this we can write as HLC by K. This is what? This is Biot number, and this is what? This is Fourier number. Okay. So obviously now the answer is, it is a combination of Biot number and Fourier number. Option A. Let us proceed to the next question now. A fin of length L protrudes from a surface held at a temperature of T naught. That is, the base temperature is T naught. Higher than the ambient temperature, that is T ambient, TA. The heat dissipation from the free end of the fin is stated to be negligibly small. What is the temperature gradient dT dx at x is equal to L at the tip of the fin? Anyone is having any doubt in order to understand this question? Yeah, it's option A. So there is no nothing to understand here, as the heat dissipation from the free end is negligibly small. So the temperature gradient will be 0. You're having any doubt, then do tell me. You're understanding this, right? The heat, how it will take place, like it is the base temperature and this is infinite, like the ambient temperature here, right? So if heat dissipation is not taking place, then this will be like at the surface of the tip. If I take that Ts is the temperature of the surface of the tip, this will be almost like it no heat dissipation is taking place, so this temperature won't be decreasing, it will be close to the temperature of the base. So if this is also Tb, then Tb minus Tb, this will be 0. Okay, let us proceed to the next question now. Which one is the characteristic length to be considered for cylindrical object of radius r and length L to calculate the Biot number? Anyone? Okay. Yeah, A it is. So how? The same way that the previous question we have already done, like that. So the characteristic length is V volume upon surface area, that is pi r square L. Okay. This is 2 pi RL, as only like slant surface area we are taking, this surface area we are taking. Like heat is like dissipating from this surface. So 2 pi RL is surface area, this is R by 2. That is option number A. Now the next question. The questions are relatively simple today. So a hot metallic spherical object of radius 10 mm is suddenly placed in a stream of air of 20 degrees Celsius, and the thermal conductivity of the sphere is 22 watt per meter Kelvin. That is, thermal conductivity is 22 watt per meter Kelvin, and the convective heat transfer coefficient, that is H, is equal to 500 watt per meter square Kelvin. The initial temperature of the object is 110 degrees Celsius. So if this is a spherical object, just 1 second. If this is a spherical object and its temperature is 110 degrees Celsius and ambient temperature is 28 degrees Celsius and the radius is 10 mm. The initial temperature is 110 degrees Celsius. Lump system approach can be applied for the system. That is, we have to check for what? For Biot number. If the first, for every question, if it is applied also, we have to check the Biot number whether it is applied or not. So now we have to choose the correct one. Okay, so this is a true or false. So we have to check whether the lump system approach can be applied for this system or not. So we'll go for checking the Biot number. Anyone? It will be B. Have you checked for the Biot number? One have said true, one have said false. Let us wait for 10 more seconds to check whether anyone is replying or not. Okay. It will be true actually. So how? So first, Biot number we need to check. And Biot number is HLC upon K. So LC is volume upon area again. So that is for sphere 4 by 3 pi r cube upon 4 pi r square. So that is r by 3. Biot number came out to be HR upon 3K. So 500 into 10 into 10 to the power minus 3 into 3 into 22. So this is 0.075. That is Biot number is less than 0.1. Right. So we know that for Biot number less than 0.1, lumped parameter approach, that is lumped parameter model, can be applied. So here lumped parameter approach can be applied. So what is said? It will be true. That is option A. Now let us proceed to the next question. The ratio of the conductive resistance of the solid to the convective resistance of the fluid is defined as which one of the following? Yeah, it will be. So we already have learned here again here. So this is what in the previous class we have seen that this is conductive resistance to the convective resistance, as we can write here as 1 upon K by LC, and here we can write as 1 upon H. This is the convective resistance, this is the conductive resistance. So Biot number is a ratio of the conductive upon convective resistance. Question number 7. That is, a solid sphere of radius 1 centimeter and initial temperature 25 degrees Celsius is exposed to a gas stream at 110 degrees Celsius. Okay. So a sphere of 25 degrees Celsius initially. This is radius of 1 centimeter. Is exposed to a gas stream of 100 degrees Celsius. For the solid sphere, the density is 10 to the power 4 kg per meter cube. The specific heat capacity is 500 joule per kg Kelvin, and the density, okay, this is density of the sphere and this is density of the gas. So the density of the gas is 0.6 kg per meter cube, and specific heat capacity is, this is for gas, this is for the sphere, this is for gas. For gas it is 1000 joule per kg Kelvin. The solid sphere is approximated as a lumped system, that is the Biot number is far less than 1, and all the specific heats are constant. If the heat transfer coefficient between solid and gas is 50 watt per meter square Kelvin, that is H is given as 50 watt per meter square Kelvin. And the time in second needed for the sphere to reach 95 degrees Celsius. Okay, so we have to need the time for which the final temperature, that is T at time T, will be is equal to 95 degrees Celsius. Simple. So, which of the following will be the correct answer? I have explained the question. Anyone who will be able to solve? Please tell me the answer. Okay, give me 30 seconds. I'm coming back. Hello? Yeah, anyone? Let me check if anyone has answered. No. Anyone who is able to solve? Or are you having any trouble to understand the question? Okay, then solve it. If you are okay, okay, correct. Solve it then. Option A. Yeah, it's correct option. Okay, let us solve this then. So, for lumped system, AH t minus t infinity is equal to minus rho v cp dt t. Now, integrating and applying the boundary conditions. At t is equal to 0, t is equal to t naught. Time is equal to 0, that is initial temperature is t naught. So if we will put this, we'll get t minus t infinity upon t naught minus t infinity is equal to minus ht a by rho v cp. So for sphere, a by v, that is the inverse of characteristic length, is equal to 4 pi r square 4 by 3 pi r cube is equal to 3 pi r. Now substituting the values, ln 95 minus 100 upon 25 minus 100 is equal to minus 50 into 3 into t upon 10 to the power 4 into 0.01 into 500. And this will give us as 902.6. So that is option number A. Okay, let us go for question number 8 now. A solid sphere with an initial temperature of Ts is immersed in a large thermal reservoir with temperature T0. The sphere reaches a steady state temperature after a certain time T1. If the radius of the sphere is double, the time required to reach the steady state is which of the following? Anyone is having any trouble in understanding? There is a solid sphere whose initial temperature was Ts and it is immersed in a large reservoir that is having the ambient temperature of T0. That is the fluid that is there, that is ambient temperature of T0. The surface reaches a steady state temperature after a certain time T1. Okay, so this is the initial time for the initial radius of the sphere. So now it said that if the radius of the sphere is double, that is the radius currently that the sphere have, this radius is been double. So what is the time now required for reaching the steady state? Kindly solve it and tell me which of the answer is correct. You solve it, I'll be back in 2 minutes. option C. Okay, let us check. Let us solve this. So, what is happening? First, we know that for lump system, HTA rho VCP is equal to minus ln T minus T naught by Ts minus T naught. So, T is steady state temperature reached after certain time. Okay. T is the steady state temperature that is attained after certain amount of time. Now, this temperature will be same for the first case and for the case 2, right? So first of all, let us find the characteristic length of sphere. So for sphere, A by V, that is inverse of characteristic length, that is equal to again 3 by R, that we have already calculated earlier. And now if we will put this in this equation, so what we will get? H T 3 by rho CPR is equal to minus ln T minus T naught by Ts minus T naught, or T upon R is equal to minus ln T minus T naught by Ts minus T naught into here rho Cp upon H3 or 3H. This whole thing will be same for case 1 and case 2. So we can consider it as constant. Like let us take it as C. Okay. So T by R is equal to C. Now for the first case we can take it as T1 R1 is equal to T2 by R2. This is for the first case, this is for the second case. So as this is constant, we can equalize both of them, and we need to find out T2, and R2 is equal to twice of R1, right? So R2 T1 upon R1. So R2 is twice of R1, T1 upon R1. This is already given. So this is 2T1. So this is T2 is twice of T1. That is the time now required will be twice of the initial time that was required. So this is option C. Correct. Okay. Now let us proceed to the next question. That is question number 9. So the feed efficiency is defined as which of the following? We on the start of the class we have already seen what the pin efficiency is all about. So I think this question is very easy for you to answer. So tell me which of the following is the correct answer. Yeah, that's option. Very good. So 9 is option A. For the next question, what we have? So, for a specific case of pin with uniform cross-section area, the resultant governing equation is this one, as we have already seen, where A is the heat transfer area and P is the perimeter. The equation is applicable for which of the following condition? One-dimensional steady-state heat flow, one-dimensional unsteady heat flow, two-dimensional steady-state heat flow, or two-dimensional unsteady-state heat flow. Anyone? this equation that we have already seen for the one-dimensional steady state. So yeah, this is correct. Let us proceed to the last three questions of today's class. So for the first question, don't go on to the language of this. This is relatively explained in a tough language, though it is a relatively very simple question. So what does it say? The power transistors that are commonly used in electronic devices consume large amount of electric power. The failure rate of electronic components increases almost exponentially with operating temperature. As a rule of thumb, the failure rate of electronic components is halved for each 10 degrees Celsius reduction in the junction operating temperature. Therefore, the operating temperature of the electronic components is kept below a safe level to minimize the risk of failure. The sensitive electronic circuitry of a power transistor at a junction is protected by its case. This case, as it said here. So the case temperature is what that is required for us in this question. So, which is a rigid metal enclosure. It's already like shown in the picture. Heat transfer characteristics of a power transistor are usually specified by the manufacturer in terms of case to ambient thermal resistance, which accounts for both natural convection and radiation heat transfer. So, this resistance that is said here, this R, this gives all the heat transfer resistance. This is a combination of all of them. There is the convection and the radiation resistance. The case to ambient temperature thermal resistance of a power transistor that has a maximum power rating of 10 watt is given to be 20 degrees Celsius per watt. So the thermal resistance also is given as 20 degrees Celsius per watt for a power rating of 10 watt. If the case temperature of the transistor is not to exceed 85 degrees Celsius, determine the power at which the transistor can be operated safely in an environment at 25 degrees Celsius. Okay. It said that the case temperature should not exceed 85 degrees Celsius. So we have to find out the power for which it won't be exceeding 85 degrees Celsius. Right. So final temperature we have to take 85 degrees. And so we will get the critical power, and we have to keep the power less than that always. So by that we can determine the power. Ambient temperature is given as 55 degrees Celsius. Anyone who is having any doubt in the question? Anyone who wants to ask any question regarding this? You are having any doubt that I can solve? You can unmute yourself and ask. Okay, if not, then solve this and tell me the answer. Anyone who is solving this? Or do you need any help? Okay, okay. Solve them. Once you solve, you ping me, okay? I'll be back in 10 minutes. Not 10 minutes, 10 seconds. Let me just get some water and I'll be back. You solve this in the meantime. Anyone have solved this? I can't see any answer. Can anyone tell me what is the power they have obtained? What will be the power that will be under the safety limit? Because the safety limit for temperature is already been given. Anyone? Is anyone there? No, not. Oh, yeah, yeah. How much was that? 3 watt. Yeah, it's 3 watt. It's 3 watt. Okay. As you have already solved, I don't think anyone will be solving anytime soon. So let us proceed with the solution then. So first of all, let us discuss about the assumptions here. First, it will be obviously a steady state operation, and the transistor case, like the case we are considering as isothermal. So its temperature at 85 degrees Celsius, because the safety limit is 85 degrees Celsius. So from the isothermal resistance network, we can see here only there is a single resistance. There is no more resistance. So resistance is already given here as how much 20 degrees Celsius per watt. So the temperature between the case, that is the case temperature, is this is the resistance and this is the ambient temperature. The case temperature is we are considering as the safety limit for 85 degrees Celsius. It is already given, and the ambient temperature is infinite, that is the atmospheric temperature to be 25 degrees Celsius. The rate of heat transfer is the temperature difference upon the resistance for the ambient. Right, case to ambient. So this is the case temperature minus ambient temperature, that is, and this is the resistance of case ambient. So this is 85 minus 25 degrees Celsius upon 20 degrees Celsius per watt, that is 3 watt. It will be simple. So the power transistor should not be operated at power levels above 3 watt, because the case temperature safety limit is 85 degrees Celsius. Okay. Let's proceed to the next question now. Very good, Sanchita, you have solved it. Uh, this is the next question, and this is the plot that you need to utilize, and this the equation that are marked here. You need to utilize to find out the efficiency that will be used in this question. Okay. So what is said, that is there is a steam in a heating system. There is a cylindrical heating system that is flowing through the tubes. That is cylindrical, whose outer diameter is 3 centimeter and whose walls are maintained at a temperature of 120 degrees Celsius. The circular aluminium fins of K is 180 watt per meter degree Celsius of the outer diameter D2, that is 6 centimeter. There is a the outer diameter of the fin is 6 centimeter and of the aluminium pipe is 3 centimeter. And the constant thickness of the fin. The thickness of the fin is 2 millimeter. From that, obviously, we can find out the convection. And for the fins, everything is given. That is the diameter and the thickness. And fins thermal conductivity is also given 180 watt per meter degree Celsius. The space between the fin is 3 mm. So from that space, obviously, from the there will be heat loss through the pipe, directly from the pipe, as there is no fin present. So the interfin distance is also given, and there are 200 fins per meter length. Heat is transferred to the surrounding, that is the ambient air temperature is 25 degrees Celsius with a combined heat transfer coefficient, that is 60 watt per meter square degree Celsius. Heat transfer coefficient is also given between the pipe and the air. So determine the increase in the heat transfer from tube per meter of its length. as a result of adding pin. So how much increase in heat transfer took place when the pins are added per meter of the length? Because per meter 200 pins are there, and per meter we have to find everything per meter of the length of the pipe. So we have to make the main thing that we need to find out for adding pins, how much more heat loss we are able to get. Okay, and this from here we will get from this graph we'll be able to get efficiency of fill. Okay, I'll open this. Whenever anyone will require the graph, you can tell me. I'll switch to the graph. That's the plot. Anyone is having any doubt in understanding the question? You kindly unmute yourself and ask me. And if not, I'll give you 4 minutes to solve this. No, 4 minutes is less. I'll give you 6 to 7 minutes to solve this. Because it is a lengthy question. But it shouldn't take more than 6 minutes to solve this. So I hope you are able to do that. And if you are having any doubt in understanding anywhere in the question, do tell me. I'm here only, okay? Anyone who is solving this? Okay, sure. If you are facing any doubt, Sanchita, do tell me. Mayank, whoever is facing any doubt, do tell me.
Ma'am, can you show the graph?
Okay, just 1 second. Are both of them visible? Just 1 second. Let me sort that out. Are both of them visible or they are too small to understand? Hello? Are both of them visible or should I maximize it?
They are very small.
Okay, make it one slide only. Yeah, this is the plot then.
Ma'am, I have a doubt.
Uh, yes, ma'am. Yes. Tell me.
Ma'am, how to calculate the fin efficiency from this graph?
Okay. See, here there are two values that you need. First one is R2 plus half T upon R1, right? Calculate that. And then,
Yes, ma'am.
uh, and then eta is also there, the equation. This equation also you calculate. And from that, you can, from graph, you can clearly see the efficiency there. Like which graph you will follow, you will understand from this. There are four graphs, right? So
Yes,
based
ma'am.
on R2 plus half T upon R1, you will understand which graph you need to pick. Like whichever value 1, 2, 3, or 5 it will be close to, you will pick that graph. And based on the eta that is given on the x-axis, that value calculate, and based on that you will find out what the efficiency will be. And that efficiency you will be using to calculate the heat transfer. Understood?
Okay, ma'am.
You can get an approximate value of efficiency, right? Then you can ask me, I'll tell you like what will be the closest one.
Ma'am, I found the efficiency, like eta I found is 0.21
0 point.
and the 21.
Okay. And
And then the That ratio R by R naught ratio is 2.067.
Ah, 2.07, yeah. Then from
Ma'am,
that, what you can get the fin efficiency?
I guess the fifth number graph, I guess.
Which one?
5. Or ma'am, that is only my doubt. Like, oh, how to choose that?
Like its value, see, you have to take the value of R2 plus half P upon R1, right? You got
Yes,
the
ma'am.
value of 2, approximately equal to 2, so you will choose the 2 now graph.
Okay, ma'am.
So that graph you will choose, you know the eta value, and just you check what will be the efficiency. Anyone is having any doubt? Hello? Okay, okay. Solved then.
Ma'am, can you show the question again?
Okay.
Ma'am, is the answer 9102.85? Like close to that.
9?
9102.85.
No. Uh, just 1 second. You have to find out the ratio, right? Okay, efficiency you may or may not find out. But you have to find out the increase, right? What you found out without fin, the heat transfer without fin.
No, ma'am, wait a minute.
You have to find out the difference. One will be with fin and one will be without fin. And with fin also there will be two parts. One will be the fin portion, another will be the spaces between the fin.
Yes, ma'am.
Hmm. So tell me what for the fin you have found out. Heat
Ma'am,
transfer with fin and
without fin was 30.78.
no, it's wrong. It won't be
Ma'am, I
30.78.
will calculate it.
Without fin, just wait 1 second. It will be area of fin, area of no fin. That is when fin is not present. So I have just denoted it
Yes,
as
ma'am.
no fin, nothing else. So it will be base temperature minus infinity. So base temperature is 120 and infinity
120 minus.
that is the ambient temperature is 25.
Yes, ma'am.
And the area is pi d1l. D1 is the pipe, the outer diameter of the pipe. So this is 3, that is 0.03 meter,
Yes, ma'am.
right?
Yes, ma'am.
So this came out to be pi dl. Pi dl means pi into 0.03 into l, that is 1. For 1 meter we took only, because we don't know the length, right? So
Yes, ma'am.
everything that is required has been asked per meter, as you can see in the question, per meter of the length. So per meter of the length, so we will take length will be 1 meter, right? So from here we will get the area, and
Ma'am, but
area if we'll put, and
ma'am, we will assume that 1 centimeter,
1
like
meter.
1 meter. Ma'am, we will assume that. Oh, it is given. Yes, ma'am.
It's given, no,
Yeah,
per
yes, ma'am.
meter.
Yes, ma'am.
So
Yes,
we
ma'am.
will take 1 meter. So
Yes,
everything
ma'am.
that will be calculating will be per meter, because in question per meter is only asked, per piece is not given. So you have to
Yes,
find out
ma'am.
everything for per meter only. What you have taken length?
Ma'am, I thought it is the space between the fins, like
No, it is not the length only.
3
It is
millimeter.
just it is
Yes.
the spacers is required when you will find the heat transfer in the fin. So there'll be two parts over
Okay.
there. One will be for fin, another will be the portions between the fins. So for that you
Yes,
have
ma'am.
required that distance. So you
Okay.
calculate again the heat transfer for no fins, that is when fins are not used, and for the fin also same per unit per meter will be there. Wait, let
Okay.
me calculate again.
Ma'am, that without fin is coming to be 0.536.
0 point. There won't be any 0 point. Where you have gone wrong.
Ma'am,
What area, like what you've taken, like what area you found out? What is the area?
ma'am, area will be 2 pi d. Sorry,
2 pi d.
pi d, pi dl, and then h will be multiplied that heat transfer coefficient.
Then
Then
temperature will be zero.
into the temperature, that difference is coming out to be 95.
Mm-hmm. What you have taken is pi d. What is the d?
Ma'am, d is 0.03.
Hmm. So then what is the area now? What area you found out? What is the area? Pi d into area, it
9.4.
is 1.
Yes,
Hmm?
ma'am. Ma'am, 9 point. Oh, ma'am, now. Ma'am, yes, I realized my mistake.
Yeah, yeah.
Ma'am, 536.94.
Hmm? Yeah, it is 537 approximately. Now, you see the efficiency of circular fin attached to the plot. So first we have to find out the length of the fin. So
Yes,
how
ma'am.
can we find that out? Tell me. Length is the fin. It is annular fin, right? So this will be the length. That is this distance from the base to the tip. What is the length?
Ma'am, the screen is not visible. I guess my net is running slow.
See, there are two diameters that is given. One is for the fin, the outer surface of the fin, and one is for the outer surface of the annular cylinder. Right, that is a tube. So, what will be the length now? And take into notice this is diameter, not the radius. So, from that, from the difference, you can easily find out the length. And from that length, you can find out the R2 plus half T upon R1. Hello? Anyone there? Actually, we have one more question left. We have to complete this question fast and then we'll proceed to the last question of today's session. Okay, you solve it. You have noted down every value, right? You solve it on yourself. Anyone who have solved this? Hello? Anyone have solved it? It's been 20 minutes on the same question.
Ma'am, 110.34 kilowatt.
This is which one?
Ma'am, the total increase, like total
Mm,
answer.
no, it's not. It's actually much higher.
Ma'am, like,
If it
ma'am,
is
it's in
watt,
kilowatts. So,
kilowatt is, if it is kilowatt, then it will be much lower. Okay. Tell me what you found out to be the efficiency be. That is from the plot.
ma'am, I took 0.56.
How come 0.56? It won't be, na?
Ma'am,
It will be much higher. Just wait. See, it is one, like almost two, right? So the second graph you will
yes, ma'am.
follow. And your efficiency is sorry, eta, that is the x-axis, is when you will found out, like when you will find out it is close to, you have also found out to be 0.21, right? So mine came out to be 0.207. So it is close to zero. So if we will take from x-axis to the graphs, like the second graph or anywhere, like it is almost close to, like everything are close together at 0.2. That is, it is the, when it is 0.2, see, from 0 to zero point 0.5, then zero point 0.5 to zero point 0.5 to 1, that is the gap is of zero point 0.5, right? So it will be almost half, less than half. uh, it will be almost point half is 0.25, so it will be less than half. So if it will be less than half approximately, let me show you. Approximately, I'll mark it around. Just 1 second. See, it will be, this portion is 0.25, right? So this portion is 0.25, and so we need, like this. So if it is 0.25, so if we will mark it again, we need zero point 0.2, right? So it will be approximately around this. So if we will extend this, it will be almost here, right?
Yes, ma'am.
If it is almost here, then this is a gap of 20, right? So that means it will,
Like, we will take like
here,
0.96 or
yeah,
95.
95, yeah, correct. Cause this is coming around here. If we will extend it
Okay,
again,
ma'am.
second graph, right? So here, almost around, yeah. So it will come out to be 0.95 approximately. Understood? So efficiency is
Yes, ma'am.
0.95.
Yes, ma'am.
Okay. So efficiency is 0.95. Now, what you need? The total fin heat transfer. So for total fin heat transfer, you first require the area of the fin. So for the area of the fin, there are two areas, right? First is, because this is two dimensional, there nowhere it is said that is it will be one dimensional heat transfer. So only for the tip of the fin we can't take. We have to take this region also,
Yes, ma'am.
like this annular region also. So for the annular region it will be 2 pi R2 minus R1. That is, R2 means the outer diameter of the fin, and R1 means the outer diameter of the tip. So that will give the area of this portion. and the area of this portion is just the perimeter of the fin, that is 2 pi r into the thickness, that will give this area, right? In the same way we do for
Yes, ma'am.
cylinder, 2 pi rl. So this will be 2 pi r t. T is the thickness. So this will give the total area of the fin, and from that
Yes, ma'am.
into the fin efficiency will give us the into the total temperature. What is the temperature? The here we have considered the temperature maintained, the walls are maintained, and wait, K is too high, so we can consider that the temperature overall the fin is at base temperature, right?
Okay,
So
ma'am.
this everything will be at base temperature. Then from everywhere the temperature will be same for whole structure. So it becomes Tv minus T infinity, right? So
Yes, ma'am.
this will be Tb minus T infinity. So this into area into the heat transfer coefficient into the efficiency. Efficiency we
Temperature.
already know, that
Yes,
will
ma'am.
give the total
Yes.
heat transfer for the fin. Now again, I have
Yes, ma'am.
already said there will be heat transfer for the spacers too. That is the spaces between the fin. So for that, if we consider that as unfin, so that will give us as pi d into s, that is the space, that is distance between, that is it is cylinder, right? So it will be pi d l,
Yes, ma'am.
and l is the distance between the two fins. That is, here it is
Yes, ma'am.
given as 3 mm. So it will be pi into d1, that is it is the annular region only, right? This diameter, outer diameter of the pipe. So that will
Yes,
be
ma'am.
this diameter, and pi d into L. L will be the space between the two region, because we need per meter, right? So per meter, if we will consider one spacer, then we will multiply with how many number of fins we have. Same way,
200.
how many number of fins, so that like we can do that all together, right? Because in class we will just take the whole heat transfer and we will just multiply it, that is the heat transfer of the spacer and of the fins, and we will just multiply it with this. For like for one set of fin there is only one spacer, right? So we will just take the distance between that set of fin. So if we will take the distance, that will be the length of this region, this area. So that is 3 mm. So pi into 0.03 meter into 0.003 meter. That is the length.
Yes, ma'am.
Now that into the same temperature difference, Tb minus T infinity, into heat transfer coefficient will also be same. So that will give us
Yes, ma'am.
for the unfin region, that is for this spacer. And that whole addition of both two, for the fin and for the unfin region, into the total number of fins, that is 200 per meter, right? So this will give us the total for the fin region, like when fin are there on the pipe, and that minus the previous one for where fins are not used, that will give us the total fins.
Ma'am, that space and that what that 0.031, it will come as 1.61 something.
1 point, the spacer,
61. Yes, ma'am.
1.61. Yeah, correct, 1.61 only. Now you find out for the fin in the same way, and just all you add both of them and you multiply with the total number of fins. That will give you for the fins. For the
And it
fin, you
will
just have to
like
multiply with efficiency. Efficiency we already got as 0.95.
ma'am, will it come out to be 1 1? Ma'am, the total increase. Ma'am, final answer
Hmm.
11272.16,
No,
near to that.
no. You tell me what you find out to be heat transfer. What is for the fin? For the fin region.
Ma'am, ma'am 25.
Yeah. Then add both of them, 25 plus 1.6, and multiply with it with 200. What you found out?
8050.
Mhm. Multiply it with 200. 2.5 plus 1.6 into 200. What you will get? For the helix
805.
crystal? No,
Yes, ma'am.
no. It's way too less. It will come out to be 5320. And for without fin, you have already found out what is the value for without fin.
537.
So 5320 minus 537, it will come out to be 4783 per meter of the tube length, and that is only required, right?
Yes, ma'am.
Okay. Now, can you find out the overall effectiveness of the fin tube? What the value will be? Effectiveness. Remember the formula. It is just the ratio. Give me the value for the effectiveness.
0.046.
0 point? How come?
046. Ma'am, uh, like with fin divided by without fin.
With fin, what is the value? How come it is less than 1? Effectiveness will be always greater than 2, otherwise the fins won't be applied. We won't be even,
Yes,
there's
ma'am.
a criteria, right? Check again.
8.90.
Hmm, almost 9.9. Okay, 5320 upon 537. It will come out to be 9.9, approximately it will be 10. So it is much greater than 2. That's why here in this case, addition of fin is like it is required for decreasing the heat transfer. Sorry, for increasing the heat transfer, that is decreasing the resistance. More convective
Okay,
heat
ma'am.
transfer will be, more easily the heat can be dissipated. Heat can be extracted from the pipe itself. Okay. So it's already 9:03. Let us proceed to the last question. Last question is very easy. I hope you can solve it in 3 to 4 minutes. So what is happening? A person is found dead at 5 p.m. in a room whose temperature is 20 degrees Celsius. That is, ambient temperature is 20 degrees Celsius. Then the temperature of the body is measured to be 25 degrees Celsius when found. And the heat transfer coefficient is estimated to be 8 watt per meter square degree Celsius. Modeling the body as a 30 centimeter diameter, 1.70 meter long cylinder, estimate the time of death of the person. It is very easy question, very easy. You don't need 3 to 4 minutes, more than 3 to 4 minutes to solve this. Okay, you solve. I'm coming in 2 minutes. Solve it fast. What it's showing. Actually, I am not the regular TA of this course, right? I am just allotted to take your like problem solving session. So all question about the assignments, you have to refer to the respective TAs for that. There are two TA who have been allotted for that. You have to ask them out. Either mail them like mail to the NPTEL IT Madras, or you can mail the individual TAs. I don't have any idea about that. Okay, you solve. I'm coming in 2 minutes. Hi, anyone have solved? Anyone? Okay, I forgot to solve the previous one, right? I've just said you how to solve. Okay, okay. In the meantime, then let me solve the previous question. Okay, let me open the previous question first for others to refer to. I don't know who have solved, but let us solve that one first. So for this, the circular aluminum fins are to be attached to the tubes of the heating system. This will increase the heat transfer for the adding fins, obviously. So the assumption here we are taking is steady operating condition and the heat transfer coefficient is uniform for the entire fin surface, and thermal conductivity is constant, and the heat transfer by radiation is negligible. So first is, this is question number 12, right? First is area with no fin, that is when fins are not attached. So that will be pi d1L, that is pi 0.03 meter into 1 meter. As we need to find per meter of length. So this came out to be 0.0942 meter square. Heat heat flow, that is for no fin, that is when fins are not attached. This is H, area of no fin, and TB minus T infinity. So this is 60 watt per meter square degree Celsius, 0.0942 meter square, 120 minus 25 degree Celsius. This is 537 watt. The efficiency of circular fins attached to circular tube is given in the plot, right? The plot that is given here. Now let us refer to this. First, what we need to find out? First, for this plot to be referred to, first we need to find out the length. That is half d2 minus d1. That is the length of the fin. This is annular fin. So its length will be like R2, that is the radius, outer radius of the fin, minus R1, that is the outer radius of the pipe, or like half of d2 minus d1, anything. So it is half of 0.06 minus 0.03, that is 0.015 meter. So this is the length. Now from the plot we need to find out R2 plus half T upon R1. So that is R2 is outer radius of the annular fins. So this is 0.03 plus half of thickness of the fins is 0.02 into 0.02, 002 in fact, and this is 0.015 meter. This is for the outer diameter of the pipe. And it is radius, that is outer diameter of the pipe is 0.03 divided by 2, that is 0.015. So this came out to be 0.07, 2.07 meter, not meter actually, 2.07 only, it is dimensionless. Okay, now eta is equal to, we need to find out eta, as in x-axis it is eta. So L plus half of T root over H by KT. Everything is given only here, we just have to calculate. 0.015 plus half into 0.002 meter into 60 watt per meter square degree Celsius upon 180 watt per meter degree Celsius into 0.002 meter. This is whole root, right? So this is half square root. This, just one second. Just one second. That is closed actually. Still. So where is it? We were at eta, right? Eta is L plus half of T root over H upon KT. So that is 0.015 plus half of 0.002 meter into root over 60 watt per meter square degree Celsius upon 180 watt per meter degree Celsius, 0.002 meter. This came out to be 0.207. Now, from the graph, as I've already shown, how to find out eta efficiency of fin, that is efficiency of fin. It is 0.95, right? So now area of fin we need to find out. So that is 2 pi r2 square minus r1 square plus 2 pi r2t. So that is 2 pi 0.03 meter whole square. Just one second. Okay. Area of fin we were finding out, right? So eta efficiency came out to be 0.95. My writing pad is malfunctioning, sorry for that. So area of fin came out to be 2 pi r2 square minus r1 square, that I've already said that the whole surface of the fin will be calculated, right? So there is this surface, this is the, let's suppose this is the pipe, this surface we are calculating now, 2 pi r2 square minus r1 square plus this surface is also there. So this surface is plus 2 pi r2t. So that came out to be 2 pi 0.03 meter whole square minus 0.015 meter whole square plus 2 pi 0.03 meter into 0.002 meter. This came out to be 0.00462 meter square. This is Q fin, that is eta, that is efficiency of fin into heat flux of fin, maximum heat flux of the fin, right? So maximum is when we will consider the whole surface of the fin is at the temperature of the base, that is the temperature of the pipe, and efficiency will give how much it is at extracting, right? Like how much it is extracting as compared to the maximum temperature difference, because obviously this area is not constant. So as this area is not constant with moving in this direction, the temperature will decrease. So we don't need to find the temperature, as we have already found out the efficiency. The efficiency multiplied the maximum fin heat flux will give us the actual heat flux or heat transfer, right? So this is 0.95 into 60 watt per meter square degree Celsius into 0.00462 meter square, that is the heat transfer coefficient, into 120 minus 25 degrees Celsius. So this came out to be 25 watt. Now heat transfer from the unfinned portion, that is, if these are the fins, this spaces between the fins. So from that portion we need to find out the heat
Ma'am, your
transfer.
writing pad is not visible.
What? From this much time it was not visible. Okay, just wait. Is visible now? The screen is
Yes, ma'am.
visible, right? Now writing pad is also visible.
Yes, ma'am.
Okay. Okay. It is a lengthy problem though. See, actually the writing pad was malfunctioning though, but we have find out we have found out 537. Let me use some other color. This 537 is the without fin. What is the heat transfer? And with fin also we need to use the efficient plot for using the plot. We needed to first find out the L. So L is half d2 minus d1, and that came out to be this. And from the plot we also need what? We also need first of all which curve we will follow. So for that we need r2 plus half of t into r1 sorry upon r1, right? So this we have calculated, we found out to be 2.07. And then we need to also find out eta, that is in the x-axis. So eta the formula is given in the plot itself. So we found out that and from that we found out I've already shown you earlier what how the efficiency will be found out. So efficiency we got to be 0.95, right? So now first for finding out the heat transfer for the finned case, so first we need to find out the area of the fin, and there will be two cases, that one is the spacing between the fin and another one is fin. For the fin, this is the area. Like if this is the fin, there will be heat transfer from this area, and also from this the top area of the fin. Like if this is the fin, right, if this is the annular region, there will be heat transfer from this portion and this portion as well. Okay, so from this portion this is the area, and for this portion this is the area, 2 pi r. So this came out to be the whole area, and now we found out the heat for the fin, the heat transfer for the fin. For the fin, it is efficiency of the fin into maximum. So the maximum will be from the base to the ambient. So that is the maximum heat transfer. But the fin will all based upon its efficiency, it will transfer that amount of heat only. So as we have already found out the efficiency, we don't need the actual temperature change of the surface. So we can use the fin efficiency. So efficiency is 0.95, and this maximum is uh, 120 minus 25 into h is 0.00462. Sorry, h is 60, and area is 0.00462. So from that we found out that the heat transfer is 25 watt for fin, when the fins are used. Now what we need now, we need for the unfinned area, that is for if these are two fins and this is the spacing between the fin, for that area we need to find out the heat transfer. So for unfinned, this is pi d1 into s is the space between the fin. So this is pi 0.03 meter into 0.003, this is the length. So we'll just consider that as a simple cylinder, and it area came out to be this is simple cylinder is pi d l, no, and l is the distance between the two fins. So this came out to be 0.000283 meter square, and the heat transfer for this unfinned region is h into a unfin into tb minus t infinity. So this came out to be 60 watt per meter square degree Celsius and 0.000283 meter square and 120 minus 25 degrees Celsius. This came out to be 1.60 watt. Now the total for the finned condition, the total is, there are 200 fins per meter. So that into 1.60, that is unfinned region, and the finned region, that is 25. So this is the total watt. This is 5320 watt. Now we need to find out the increase, that is total, the heat transfer total of fin minus the heat transfer total of no fin, that is 5320 minus 537. This came out to be 4783 watt per meter of the tubelet. We also have calculated the fin efficiency overall, that is just the heat transfer of total of fin upon the total of no fin. That is how much have fin helped us to extract the heat from the pipe. So it must be obviously greater than equal to 2. So it will be, if it is greater than or equal to, then only we will say okay, you fabricate fin. Otherwise the cost of fabricating will be like it won't be covering for the heat loss, like heat that is extracted. So if you are using fin, it should be greater than or equal to 2. So this came out to be 5320 watt upon 537 watt is equal to 9.9. Okay. Now for question number 13, who have solved question number 13?
Ma'am, that ma'am, the time is coming out to be 43859 seconds. Like it is equivalent to 12.18 hours.
Yeah, yeah, correct.
So
It's correct.
before that,
Mm-hmm.
like before 12.18 hours before 5.
Have you calculated the biot number? How much it came out?
Ma'am, no, I did not calculate.
For any lump parameter model, if it's not set in the question, then
Yes,
you
ma'am.
can't consider it as a lump parameter system. Okay.
Yes, ma'am.
So, okay. Let us first proceed. First, we will calculate the biot number for any lump parameter model problem. So, for biot number, we need to find out the characteristic length first, as it is we are considering as cylinder. So, it will be pi r naught square L upon 2 pi r naught L. But here it is a real system, so we are considering the circular cross sectional area also. So, 0.15 meter whole square, this is 1.7 meter, and this is 2 pi 0.15 meter, 1.7 meter plus 2 pi 0.15 meter whole square. This came out to be 0.0689 meter, and biot number came out to be HLC by K. So this came out to be H is 8 watt per meter square degree Celsius, and LC is 0.0689 meter, and this is 0.617 watt per meter degree Celsius. This came out to be 0.89 greater than 0.1. So this is greater than 0.1. So for learned parameter system, we need less than 0.1. So obviously this here learned parameter system is not applicable. But it is the simplest model for transient system, right? For any transient model, it is the simplest equation or simplest model to go around with. So this will give us, even if it is not applicable, it will give us a rough idea about the time of death of the person. So we are following this to get an approximate idea of time of death. So this is like, if we know the equation as t minus t infinite, that is ambient temperature, and the initial temperature minus the ambient temperature. This is E minus BT, right? So if we consider this B will be HAS upon rho CPV, that is H upon rho CP LC, that is V upon AS is LC, right, the characteristic length. So this is 8 watt per meter square degree Celsius upon 996 kg per meter cube and 4178 joule per kg degree Celsius and 0.0689 meter. This came out to be 2.79 into 10 to the power minus 5 second inverse. So if we will put in the main equation, this is 25 minus 20. 20 is the ambient temperature, 25 is the final temperature of the body, and initial is 37 minus 20. Initial is 37 minus 20 e to the power 2.79 into 10 to the power minus 5 second inverse. This is 43860 second. This is 112.2 hour approximately. So this is rough estimate of the time. So almost 12 hours, that is if it is 5 p.m. then he died about 5 a.m. Right, 5 at 5 a.m. Before. So this is a rough estimate by using learned parameter system. But anytime you use learned parameter system, before that you need to calculate the Biot number. Okay. Any doubt?
No, ma'am.
Okay, then it's way too much time. It's 9:30 already. So today we will end the class here, and I'll meet you guys next week, same time at 7 p.m. Tuesday. Okay. So solve the assignment on like these questions on yourself and the class assignments. And whoever is having doubt for the class assignment, you can contact NPTEL Madras directly, or you if the email IDs are I think provided to you of the TAs, the respective TAs for the assignment section. So or you can even give the question to the like what doubts you have into the there is one place for you, right? One Google group where you can post any question regarding your assignment. So you can post any
Yes,
question.
ma'am.
Yeah, there is the Google group. So you can join the group and you can post the question there. The regular TA will be answering you the question. If you are unable to find the question, you just post your doubt there. Like assignment 3 you are unable to find now, you just post the doubt there, they will correct it. Okay then, bye guys. I'll meet you all next week.
Thank you, ma'am.
uh now Achha. Okay then, I'm ending the meeting. Whoever is there, I don't know, like you can leave.